Think about just a simple wire carrying electricity. Seems pretty straightforward, doesn't it?
Yeah, pretty basic stuff.
But what if the actual shape of the tiny molecules inside that wire? What if that shape held some kind of hidden power, a microscopic influence on how electrons flow?
Okay, I see where you're going. Sounds a bit like science fiction, maybe.
A little, but that's exactly what we're going to dig into today.
Right, we're looking at some really fascinating new research connecting the handedness of molecules, we call it chirality, in certain superconductors, organic ones specifically.
Handedness, chirality,
Oh, okay.
and how that affects, well, some pretty potent electronic effects. Things like how electron spin interacts with the current, and this related idea called non-reciprocal transport.
Okay, chirality. So like my left hand and my right hand, they're mirror images, yeah. But you can't perfectly stack one on top of the other.
Exactly that. Simple concept, but it turns out this property, down at the molecular level, is becoming a really key player in some cutting-edge physics. And our mission today, then, is to unpack how this molecular handedness can actually lead to these powerful electronic things happening, maybe even, revolutionary superconducting devices down the line.
That's the idea. And yeah, this isn't just speculation. We're diving into some solid research published very recently, April 15th, 2025, in Physical Review Research.
Oh, yeah?
The paper's called Sturdy Spin Momentum, Locking in a Chiral Organic Superconductor. It's from Takuro Sato, Hiroshi Goto, and Hiroshi M. Yamamoto researchers at the Institute for Molecular Science, IMS, and SOKENDAI.
Got it. So for listeners wanting to cut through the jargon and just get the essence of this discovery fast, that's what we're aiming for.
Let's do it. We can start with something called Chirality-Induced Spin Selectivity. CISS for short.
CISS. Okay, sounds a bit complex.
Well, the name is maybe a bit technical, but the effect itself is really intriguing. Imagine electrons moving through these handed molecules. The molecule's handedness, its shape, basically acts like a filter. It strongly prefers electrons spinning in one particular direction over the other.
Like a tiny turnstile, letting one kind of spin through more easily.
Exactly like a turnstile. That's a great analogy. And here's the really interesting part, the kicker maybe. This happens in organic materials, stuff made mostly of light elements like carbon, hydrogen.
Right. And that is the bit that seems counterintuitive, isn't it? Because normally when you want to mess with electron spin, you think heavy elements, big atoms.
You're spot on. The traditional way involves what's called spin-orbit coupling. That interaction between the electron spin and its movement around the nucleus, it's just much, much stronger in heavy elements.
So finding this strong spin effect, this filtering in light organic stuff, that suggests a totally different mechanism is at work, right?
Precisely. It's a way to influence spin without needing those heavy atoms. The chirality itself, the shape, is doing something special. It's fundamentally different.
So the molecule shape does the job instead of a heavy atom. That's a big shift. But the research also mentions it's been hard to actually measure the CISS effect accurately. Why is that?
Yeah, the practical side. Detecting and really quantifying the spin filtering due to shape alone is technically very tricky.
Okay.
You need incredibly sensitive measurements to sort of isolate the CIS effect from all the other electronic noise happening, like trying to hear a whisper in a really noisy room, These very specialized tools.
Gotcha. So scientists suspected chirality could matter for spin, but pinning down the details was tough, which I guess brings us to the specific material they studied. This NCS. That's much easier. It was really the perfect candidate. Why? Because it's an organic material. We already knew it had this chiral structure, and it's a known superconductor.
Okay. So all the pieces were there. Exactly. And crucially, this CISS effect, this spin filtering, had actually been seen before in its superconducting state. So it was like the ideal lab bench to really probe deeper into how chirality and superconductivity connect. And, could this handedness cause other weird electronic stuff?
And it turns out it could.
Right.
They found this giant non-reciprocal transport. And that sounds pretty intense. What does non-reciprocal transport actually mean? And why giant?
Okay, non-reciprocal transport. Think of it like a one-way street, but for electrical current.
Okay.
Normally, resistance is the same, whether current flows left to right or right to left. Simple. But in these non-reciprocal materials, the resistance changes depending on the direction.
Like it's easier to go one way than the other.
Precisely. This usually happens in materials that lack certain symmetries and often involves, again, that spin-orbit coupling, typically in specific inorganic materials like polar crystals.
Right.
Now, the giant part. What was really astonishing here is that in CISS, this organic superconductor, they saw an unusually large non-reciprocal effect, way bigger than standard theories predicted, and actually bigger than what's seen in some of those specialized inorganic superconductors.
Wow. So this organic stuff made of light atoms is showing a stronger one-way street effect than materials almost designed for it.
Exactly. The paper actually has some visuals comparing it, and the difference is really striking. It's extraordinary for an organic crystal.
That really is amazing. How can simple molecular shape have such a massive effect? The researchers think the key is that the chirality acts like an effective spin-orbit coupling. What does that mean, effective?
Yeah, that's their core interpretation. Essentially, the molecular handedness in CISS dramatically ramps up the interaction between the charge, the flow of electrons, and the electron's own spin.
Okay.
So the chiral shift creates this local environment that, for the electron, feels like the strong spin-orbit coupling you'd normally only get from heavy atoms. It mimics it, hence effective.
I see. It's like a trick of geometry.
Kind of. And their theoretical work backs this up. They found the huge non-reciprocity they measured just couldn't be explained by the basic electronic properties, the standard band structure stuff. You needed this boosted, chirality-driven spin-orbit interaction.
And there was something else too, right? Something about the Cooper pairs.
Yes, exactly. They also found it requires what's called a spin triplet component in the Cooper pairs.
Okay, Cooper pairs. Those are the electron pairs that let superconductors carry current with no resistance. But spin triplet, what's different about that?
Right. So in most vanilla superconductors, the two electrons in a Cooper pair have their spins pointing in opposite directions, up and down. That's called a spin singlet.
Okay, singlet, opposite spins.
A spin triplet component means that some of the electron pairs actually have their spins aligned, both pointing the same way. That's much less common, especially in this class of organic superconductors.
So the chirality, acting like this strong spin-orbit coupling, is actually changing how the electrons pair up, making these unusual triplet pairs form.
That's the implication. It suggests the underlying physics of the superconductivity itself is being altered by the molecular shape, leading to this more complex pairing state.
This just gets more and more interesting. So chirality isn't just like nudging the electrons, it's fundamentally changing their behavior, how they partner up in the superconducting state.
It seems so.
And that leads to another cool observation they made, the superconducting diode effect. What's that? And how good was it in this CISS material?
Right, the diode effect. It's a direct consequence of that non-reciprocal transport we talked about, but in a superconductor.
Okay.
Think of a regular diode in electronics, lets current flow one way, blocks it the other. A superconducting diode aims to do that for supercurrent, the zero resistance kind. Ideally, supercurrent flows freely one way, but gets blocked or meets resistance going backwards.
A one-way street for supercurrent.
Exactly. And they observed this in CISS with extremely high efficiency of up to 5%.
5%. Is that good? How does it compare?
It's actually really good, especially considering this is an organic material. The initial reports for inorganic polar superconductors, the ones sort of designed for this, were around 6%.
Wow, so it's right up there. An organic material competing with specially engineered inorganic ones.
Pretty much neck and neck in these early stages.
Yeah.
It really hammers home the potential power of using chirality.
That's incredible. So, okay, the researchers basically wrap this up by saying it all points to a non-trivial coupling between spin and current driven by chirality. What does non-trivial really mean here? Is it just not zero?
Well, it means more than not zero. Non-trivial here means the connection, the coupling between the electron spin and the electrical current isn't just some weak background effect you might normally expect.
Right.
It's a significant complex relationship that goes way beyond what the standard models for these organic materials would predict. It's unexpectedly strong and has real consequences, like driving that giant non-reciprocity and, as we discussed, helping explain why those unusual spin triplet Cooper pairs are forming.
So it's a surprisingly strong, impactful connection, not just a footnote.
Exactly. It's a major player in the physics here, all thanks to the molecule's shape.
Okay, so we've got this amazing link. Molecular shape, powerful electronic effects. What are the sort of bigger picture implications? Why should people listening, maybe interested in future tech or just fundamental science, really pay attention to this? Could it lead to, say, more efficient electronics?
I think absolutely. On a fundamental level, this research really tackles a long-standing challenge, which was how to properly measure and understand the CISS effect.
Right, the difficulty in pinning it down.
Yeah. By linking it directly to these measurable things, the non-reciprocal transport, the diode effect in a superconductor, they've given scientists a powerful new toolkit to study it. And that alone could have a profound impact on both physics and chemistry.
Okay, so better fundamental understanding.
And it provides a totally novel perspective on superconducting rectification, that one-way street effect. That field has been almost entirely focused on inorganic systems. This cracks open the door to organic materials.
Bringing organic chemistry into the game for these kinds of effects.
Exactly. And yes, thinking about applications, highly efficient superconducting diodes may be built from these potentially easier to process organic materials. That could definitely impact energy efficiency in future specialized circuits.
You could spark a whole new direction in material science.
Yeah.
Looking at chiral organic stuff for electronics.
I think it really points that way. It suggests we should be casting a much wider net, looking seriously at all sorts of materials with chiral structures. We might find completely new electronic or magnetic properties we haven't even thought of yet.
Yeah.
And ultimately, yes, this could absolutely pave the way for innovative superconducting devices and functional materials that harness these chirality effects.
Okay, let's try and crystallize this. The real kind of wow moment here is realizing that something as seemingly simple as the handedness of a molecule chirality can unlock these incredibly powerful spin phenomena in superconductors.
Yeah, effects that can seriously rival, maybe even beat, what we see in materials loaded with heavy elements, which is just unexpected.
Yeah, really remarkable.
And the potential for this discovery to spawn completely new kinds of superconducting devices, things with functionalities we haven't achieved before, that feels much more tangible now. Think about advanced quantum computing components or super-sensitive magnetic field detectors.
It really makes you wonder, doesn't it? Could the secret to the next generation of advanced electronics lie not just in finding new elements or compounds, but in, well, carefully controlling the shape of the molecules we already use?
It's a fascinating thought. What other fundamental properties might just be hiding there in plain sight, waiting for us to look at them from a different angle, like chirality has shown us here?
That link between the tiny world of molecular shapes and the big performance of advanced electronics, definitely something to think about.